Have you ever wondered why the moon never seems to turn? Night after night, it hangs in the same position, showing us the same calm, silvery face as if frozen in the sky. But is it really still, or is there a secret motion hidden beneath that silence? A rhythm so precise we can't see it at all. Tonight, we'll travel into that mystery, uncovering how the moon's stillness is, in truth, a dance billions of years in the making. Before we start, tell me in the comments, where are you listening from, and what time is it for you right now? I read every reply, and it helps me understand who's watching and when. If you want to jump to a specific topic, I've divided this video into clear parts. All chapter timestamps are listed in the description so you can go straight to the section you need. Otherwise, let's go step by step. We'll keep the pace slow, the explanations clear, and the numbers simple enough to follow without a screen. My goal is that by the end you'll understand why the moon keeps the same face toward us, and if you're listening at night, that you'll be relaxed enough to fall asleep. Take a breath, get comfortable, and let's begin. For as long as humans have looked up at the night sky, the moon has seemed completely still. It rises, it sets, but the same side, the same pattern of craters and shadows always looks back at us. It feels like a silent face carved in stone, unmoving for billions of years, but that stillness is an illusion. The moon is not frozen in place. It is moving, constantly, in one of the most precise and balanced motions in the solar system. In reality, the moon spins on its axis once every 27.3 days, exactly the same time it takes to orbit Earth once. That's why we only ever see one side. As the moon travels around us, it turns just fast enough to keep the same hemisphere facing Earth at all times. This perfect synchronization is called tidal locking. It's not a coincidence or magic, it's physics, shaped by gravity and time. To understand it, we need to look back about 4.5 billion years, when the moon first formed. Back then, it was spinning much faster, maybe once every few hours, but Earth's gravity was already pulling on it, tugging unevenly on the parts of the moon that were closer and farther away. Over time, the constant tug created tidal friction inside the moon's rocky body. The friction worked like a cosmic brake, slowly draining the moon's spin energy and turning it into heat. Imagine spinning a ball of clay while someone gently presses on one side. The shape stretches, the spin slows, and eventually it starts to turn in rhythm with the force pressing against it. That's what happened between Earth and the moon. The braking continued until the moon's rotation slowed enough to match its orbit. At that exact moment, the lock clicked into place. From then on, only one face would ever look toward Earth. NASA's Lunar Reconnaissance Orbiter confirms that this synchronization is nearly perfect. Every 27.3 days, the moon completes one rotation, no more, no less. To us, it seems motionless, but that's only because we're moving in sync with it. From space, you could watch the moon gently turning, its spin and orbit perfectly matched, like a dancer who never breaks step. Scientists call this state synchronous rotation, and it's one of nature's most stable configurations. The balance is so precise that even small changes in speed or distance correct themselves over time. Gravity constantly pulls the system back into harmony. There's even a way we can see that it's not truly still. If you observe the moon carefully over a month, you'll notice that its face seems to shift slightly side to side and up and down. This small motion is called libration. Because the moon's orbit isn't a perfect circle and its axis is slightly tilted, we can peek a little around its edges. Thanks to libration, we can actually see about 59% of the moon's surface from Earth, not just half. That tiny sway is proof that motion never fully stops. Even in apparent stillness, the moon is constantly balancing the forces of spin, orbit, and gravity. The Grail mission, which mapped the moon's gravitational field in detail, revealed something even deeper. Inside the moon, variations in crust thickness and density match exactly what models predict for a world that's slowed through tidal locking. In other words, the evidence of this process is written into the moon's rock itself. The fractures and internal stresses are permanent scars left by billions of years of gravitational tugging. Scientists often describe tidal locking as nature's way of achieving stability through loss. The moon gave up its rapid spin but gained a long-term, harmonious orbit. That exchange created a balance that has lasted for billions of years. And this balance doesn't just affect the moon, it shapes Earth. too. The moon's steady pull creates the tides that make our oceans rise and fall. It also stabilizes Earth's axial tilt, keeping our seasons regular and our climate relatively mild. Without the moon's stabilizing influence, Earth's axis could wobble unpredictably, making the planet's weather and seasons far less stable. So, the next time you see the moon hanging in the sky, remember, it's not frozen, it's moving, slowly but precisely, turning in harmony with its orbit around Earth. The stillness we see is actually a perfect balance of forces, a kind of quiet motion so steady that our eyes can't perceive it. If you could stand on the moon's near side, the side that always faces us, you would see Earth suspended in the same spot in the sky, never rising or setting. On the far side, Earth would never appear at all. Two completely different skies on the same world, divided forever by the geometry of gravity. That's the meaning of tidal locking. It's the moment when motion and time reach agreement, a balance where nothing is wasted, and nothing is truly still. The moon's calm, unchanging face is not the absence of movement. It's the result of movement perfected. Every turn, every orbit, every tide is part of that same ancient rhythm, and in that rhythm, our planet has found its balance, and our nights have found their light. Gravity doesn't roar or shine. It doesn't flash like light or burn like fire. It simply pulls quietly, constantly, everywhere. From the motion of galaxies to the path of a single pebble dropped to the ground, gravity is the silent architect of order in the universe. It's this same invisible force that binds Earth and Moon together in a dance so precise that it has lasted more than 4 billion years. To understand why the Moon remains locked to Earth, we have to return to the laws that describe how everything moves. In the 17th century, Isaac Newton showed that every mass attracts every other mass. The strength of that pull depends on how massive the two bodies are and how far apart they sit. Johannes Kepler refined that idea, describing how planets trace out ellipses and how their orbital speeds change with distance. Together, Newton and Kepler gave us the language that explains why the moon circles Earth, and why that motion slowly transformed into the perfect rhythm we see today. When the moon first formed, it spun quickly. Its day may have lasted only a few hours, but even then, Earth's gravity was tugging unevenly on it. The side of the moon closer to Earth felt a slightly stronger pull than the far side, stretching the young body into an oval shape. Those stretches created two small bulges, one facing Earth, one pointing away, because the moon was rotating faster than it orbited. The bulges didn't line up perfectly with Earth's pull. They lagged behind slightly, like a wave trying to catch up with the wind. That tiny offset made all the difference. It produced tidal friction inside the moon's rocky interior, a resistance that converted spin energy into heat. Bit by bit, the moon's rotation slowed. NASA scientists estimate that the torque created by Earth's gravity during that early period reached about 10 quadrillion Newton meters. That's an unimaginably large twisting force, enough to heat the moon's crust and mantle and even melt parts of its interior. Over millions of years, the heat faded into space, but the slowing continued. Every small shift in rotation leaked a little more energy until the moon's spin period matched its orbit around Earth. The braking stopped only when the two motions synchronized perfectly. At that moment, the moon entered synchronous rotation, its tidal lock. What had once been a freely spinning world became a partner in balance. But the energy that vanished from its spin didn't disappear entirely. It moved into the moon's orbit. Angular momentum, the measure of a body's rotational motion, transferred from the moon's rotation to its revolution. The result? The moon began to drift outward, a few centimeters each year, farther from Earth but still bound to it. We can measure that drift directly. The Apollo astronauts left mirrored panels, called laser reflectors, on the lunar surface. From observatories on Earth, scientists fire laser pulses at them and time how long the light takes to return. Those measurements show that the moon is receding from Earth by about 3.8 centimeters per year, roughly the rate your fingernails grow. It's a tiny change, but over geological time it reshapes the entire Earth-Moon system. The story of that slow movement is written in the moon's crust. Mapping by NASA's Grail mission revealed subtle variations in gravity that match models of internal heating and deformation. Regions where the rock is denser and thinner line up with the direction of Earth's ancient pull. Even now, the moon's center of mass sits about 2 kilometers closer to Earth than its geometric center, another sign of that long-term stretching. This offset helps keep the lock stable, ensuring that the same side always turns toward us. Gravity's grip works both ways. As the moon pulls on Earth, it raises tides in our oceans. The water bulges slightly ahead of the line connecting Earth and Moon because our planet rotates faster than the moon orbits. Those ocean bulges drag against the sea floor, creating friction that also converts energy into heat. The total energy lost is staggering around 3.7 terawatts every year, roughly equal to all of humanity's power use. The effect on Earth is gradual but measurable. Our planet's rotation is slowing by about 2 milliseconds per century. That means our days are getting longer, one heartbeat at a time. The energy lost from Earth's spin goes into the moon's orbit, keeping the balance intact. This exchange of energy and motion is the quiet conversation that has linked Earth and Moon for billions of years. Each tug, each tiny shift in rotation, is part of the same dialogue. The moon drifts outward, Earth slows down. Both move toward a shared equilibrium. Someday, billions of years from now, this process will reach its final stage. Earth itself will become tidally locked to the moon. One hemisphere of our planet will always face it, the other will never see it again. Days and months will merge into a single rhythm, and the tides will freeze in place. It's hard to imagine something so slow, so silent, shaping entire worlds. Yet that's the power of gravity. It doesn't need noise or speed. Over enough time, it turns chaos into order, motion into harmony. The moon's still face. The rising and falling of our tides, even the length of our days, all are the result of this invisible, relentless force that never stops working. Gravity's tidal grip is the reason the moon looks still, the reason our oceans move, and the reason both worlds will continue to evolve together. In its silence, it keeps time for the whole Earth-Moon system, reminding us that in space, even stillness is born from motion. The moon that we see tonight looks calm and steady, almost eternal, but billions of years ago, it was nothing like this. It was young, violent, and blazing hot, a world born in fire. Its days passed in a rush of motion, not in 27 days as they do now, but in only a few short hours. The moon once spun freely, glowing red-orange from the heat of its own creation. Its story begins about 4.5 billion years ago, with a collision that nearly destroyed the young Earth. A planet roughly the size of Mars, known to scientists as Theia, struck Earth at an angle and with incredible speed. The impact melted vast amounts of rock, threw molten debris into orbit, and released more energy than 1 trillion modern atomic bombs combined. Out of that debris, the moon began to form. At first, it was a molten sphere surrounded by clouds of vaporized stone. Simulations from NASA's early lunar formation studies suggest that the newborn moon rotated extremely fast, completing one full turn in less than 10 hours. That spin came from the violent energy of the impact itself, but gravity was already shaping its destiny. Even as the new world cooled, Earth's immense gravity started tugging on it. The pull was uneven. The near side felt slightly stronger than the far side. This constant stretch produced tides not in water, but in rock. The moon's surface bulged slightly toward and away from Earth, and as it rotated, those bulges shifted position. Each shift created friction deep within its interior. The rocks flexed, heated, and resisted. That resistance acted as a brake on the moon's rotation. In physics, energy is never truly lost. The energy that once made the moon spin faster was converted into heat and deformation inside its crust and mantle. Over time, perhaps 100 million years or more, that friction drained the excess spin. The rotation slowed, the orbit widened, and the young moon began to settle into balance. This transformation left its mark in the rock. The near side always pulled slightly closer to Earth, cooled differently from the far side. Its crust became thinner, allowing molten basalt to rise through cracks and flood the surface. Those dark plains we call Maria the seas that form the patterns we see from Earth are the frozen remains of that ancient lava. The far side, thicker and cooler, stayed rugged and mountainous. When NASA's Grail mission mapped the moon's gravity field billions of years later, it found patterns that matched this history exactly. Long stress lines, subtle variations in crust thickness, and density differences frozen into place. They are the scars of a world that once spun far too fast and slowly gave up that motion to the pull of its parent planet. As the moon lost rotational energy, it gained orbital momentum. The conservation of angular momentum, the rule that total motion in a system must remain constant, meant that what the moon lost in spin, it gained in distance. The Earth-Moon pair adjusted together like dancers balancing a shared step. The moon drifted outward. Earth's rotation slowed slightly. The system found equilibrium, not through stillness, but through exchange. Once the moon cooled and solidified, the balance became self-correcting. Any small disturbance and impact or internal shift would create a restoring torque, a gentle gravitational pull that brought the alignment back into place. Over billions of years, that mechanism kept the moon's face turned steadily toward Earth. Today, even after countless meteorite strikes and internal quakes, the moon's orientation changes by only a fraction of a degree. It is one of the most stable rotational states known anywhere in the solar system. The lock is not fragile, it's resilient, designed by physics itself to endure. If we could watch the moon's history in time-lapse, we'd see a wild transformation, a glowing sphere spinning rapidly, slowing with each eon, its molten surface solidifying, its rotation aligning with its orbit. Slowly, chaos would fade into rhythm. What began as a violent birth became a quiet balance. The moon's calm face tonight hides that fiery past. Every crater and every ridge carries a memory of the motion that once shaped it. Its stillness is not a sign of rest, but of completion, a perfect balance reached after ages of struggle. And if you look up at it now, remember that beneath that pale light lies a record of motion, heat, and change. The moon has not always been silent. It once roared with energy, spun in wild rotation, and glowed with molten fire. What we see today is the final chapter of that story, a world that traded motion for harmony and found peace in gravity's steady pull. For thousands of years, every human who looked up at the night sky saw the same face of the moon, the side that always turns toward Earth. Poets, scientists, and dreamers imagined what might lie beyond that familiar pattern of craters and dark plains. Was it smooth and calm like the side we see, or something entirely different? For most of human history, it was pure mystery. Then, in the year 1959, that mystery finally lifted. A small Soviet spacecraft called Luna 3 flew around the moon and, for the first time in human history, photographed the hemisphere that never faces Earth. The images were grainy and faint, but they changed our understanding of the moon forever. The far side was nothing like the near side. It was rough, mountainous, and covered with countless craters. Gone were the wide, dark plains we call Maria the seas that form the patterns of a face when we look up from Earth. Instead, the far side looked like an ancient battlefield, untouched since the beginning of time. This difference raised a profound question. Why would one side of the same world be so smooth and the other so scarred? For decades, scientists worked to find the answer, and the clues came from spacecraft that followed in Luna 3's path. NASA's Lunar Reconnaissance Orbiter, known as the LRO, later mapped the moon in incredible detail. Its data show that the crust on the far side is, on average, about 15 kilometers thicker than the crust on the near side. That thickness turns out to be the key. On the near side, the crust is thinner, which allowed molten rock from the interior to reach the surface billions of years ago. When large meteorites struck, magma flowed up through the cracks, filling the impact basins and cooling into the dark basalt plains we see as Maria. But on the far side, the crust's extra thickness acted like a shield. Even after massive impacts, the molten rock below couldn't break through. No seas of lava formed there, leaving the far side covered in bright, rugged highlands. Chemical evidence supports this story. The near side's rocks are rich in iron and titanium-heavy elements that darken the surface. The far side's crust, by contrast, contains more aluminum and calcium, making it lighter in color and harder in structure. This compositional contrast tells us that the two hemispheres cooled and evolved differently from the very beginning. Scientists believe that Earth itself played a role in this imbalance. When the moon was still molten, Earth's strong gravity may have pulled heat-producing radioactive elements toward the near side. That extra heat kept it softer for longer, allowing the crust to stay thin. The far side, farther from that influence, cooled faster and hardened sooner. Because of this, the far side has remained a geological time capsule. Its surface preserves scars from some of the earliest events in the solar system impact craters so old that they date back more than 4 billion years. The most dramatic of them is the South Pole Aitken Basin, a colossal impact site about 2,500 kilometers across and up to 8 kilometers deep. It's one of the largest and oldest known craters in the entire solar system. If you could stand inside it, the rim would curve beyond the horizon, a landscape shaped by unimaginable violence. NASA's LRO and GRAIL missions have shown that this basin may have exposed material from deep within the moon's mantle. Variations in gravity over the region match what scientists would expect from mantle rocks near the surface, evidence that the impact was powerful enough to punch through the crust itself. In 2019, China's Chang'e 4 mission made history by becoming the first spacecraft to land softly on the far side of the moon, inside the von Karman crater within the South Pole Aitken Basin. Its small rover, Yuta-2, continues to study the rocks and soil there. Instruments on board detected minerals such as olivine and low-calcium pyroxene, exactly the kinds expected from the moon's deep interior. Those discoveries confirmed what earlier missions had only suggested. The far side is a window into the moon's hidden layers. The far side's extreme environment also makes it unique in another way. Because it always faces away from Earth, it is completely shielded from our planet's radio signals. No human-made interference reaches that hemisphere, making it one of the quietest places in the solar system for listening to the universe. Astronomers dream of building radio telescopes there to detect the faint signals left over from the birth of the first stars. Of course, exploring that region isn't simple, because there's no direct line of sight to Earth. Every signal from a spacecraft must be relayed through satellites positioned above the moon. China's Queqiao satellite, launched in 2018, performs that role today, orbiting a stable point called Lagrange Point 2. It acts as a bridge between the far side and Earth, a remarkable engineering solution that lets us communicate with a world we can never see directly. Every crater, ridge, and shadow on the far side tells a story of billions of years of impacts. Unlike the near side, the far side has no partial protection from Earth's gravity. Our planet's mass sweeps up some of the meteoroids that might otherwise strike it, leaving the hidden hemisphere to bear the full history of collisions. When people call it the dark side of the moon, that's not quite right. It's not dark, it receives sunlight just as the near side does. It's simply unseen, hidden forever by the geometry of tidal locking. Yet that unseen half carries the oldest record of the moon's past, a record carved into rock by time and silence. The far side reminds us how much we still have to learn. One hemisphere shaped by fire and lava, the other by ice and impact. Together, they tell a single story of creation and endurance. The moon's hidden face is not another world, it's the other half of our own, waiting quietly beyond our sight. The moon may look timeless, but its story is still unfolding. Even now, it's slowly drifting away from us about 3 8/10 centimeters every year. That distance is tiny, roughly the width of a fingertip. Yet it's measurable and constant. It means that the gravitational connection between Earth and Moon, the same force that locked their motions together billions of years ago, is still at work today. We know this not from guesswork, but from light itself. When the Apollo astronauts visited the Moon in the late 1960s and early 1970s, they left behind small mirrored panels called laser reflectors. Since then, scientists have been firing laser beams from observatories on Earth, timing how long it takes for the light to bounce back. The results are astonishingly precise. The round-trip travel time, just over 2.5 seconds, reveals that the moon is steadily moving away. Each new measurement confirms that our satellite is drifting outward, little by little, year after year. Why does this happen? The answer lies in the subtle but powerful process called tidal friction. As Earth rotates, the moon's gravity pulls on our oceans, raising bulges of water on the side facing the moon and the side opposite it. But Earth spins much faster than the moon orbits. It completes one rotation in about 24 hours, while the moon takes over 27 days to circle us. Because of that difference, those ocean bulges don't point directly toward the moon. They're dragged slightly ahead by Earth's rotation. This offset matters. The extra pull from those misaligned bulges exerts a small forward force on the moon, giving it a little boost in its orbit. At the same time, the moon's gravity pulls back on the bulges, creating a braking effect that ever so slightly slows Earth's spin. In essence, Energy flows from Earth's rotation into the moon's motion. Earth loses spin, the moon gains distance. The exchange is constant, gentle, and measurable. Our planet's day lengthens by about 1 7/10 milliseconds per century. That's far too small to notice in daily life, but it's enough to change the rhythm of the planet over geological time. If we could watch the clock of Earth's rotation through the ages, we'd see our days gradually stretch longer and longer. Scientists have found physical proof of this slowdown in the rock record. Some ancient sedimentary formations, called tidal rhythmites, preserve layers that record the daily and monthly tidal cycles of ancient Earth. In formations dating back to the Devonian period roughly 400 million years ago, these patterns show that there were about 420 days in a year. That means each day lasted only around 21.5 hours. Since then, the rotation has slowed, and the number of days per year has decreased as each day has grown longer. This is how the Earth-Moon system maintains its balance. By conserving angular momentum, the total amount of rotational and orbital motion in the system remains constant. Energy isn't lost, it's merely moved. Earth's spin slows, and that energy becomes orbital energy for the moon, pushing it slightly farther out. Meanwhile, as the moon recedes, its orbital speed decreases. That's because a larger orbit takes more time to complete. The balance of gravity and motion adjust perfectly, as if both worlds are responding to an unspoken agreement to keep the total system stable. The process is far from gentle on a planetary scale. The constant tug of the moon's gravity on our oceans creates enormous friction against the seafloor. That friction converts kinetic energy into heat, an estimated 3 7/10 terawatts of power every year. To put that in perspective, that's nearly the same amount of energy that all of humanity currently uses worldwide. Yet it's released so gradually that we only sense it through the slow pull of the tides and the passing of time. This energy exchange is a quiet dialogue that has lasted for billions of years. It has shaped both worlds, the moon's orbit expanding, Earth's rotation slowing, their connection stretching but never breaking. The process will continue for as long as tides exist. Eventually, in the far future, it will reach a final equilibrium. Earth's rotation will slow until one side of our planet always faces the moon, just as the moon always faces Earth today. At that point, both worlds will be mutually tidally locked, turning together in perfect rhythm. One hemisphere of Earth will have the moon permanently overhead, the other will never see it again. Days and months will merge into a single cycle. This outcome won't arrive soon. It will take billions of years, but the direction is clear. The system is moving steadily toward that state of balance, step by step, centimeter by centimeter, and through it all, the relationship between Earth and Moon remains profoundly intimate, even across nearly 400,000 kilometers of space. They are connected through invisible forces that never stop working. Every high tide, every ocean wave, every gentle shift of Earth's spin is a sign of that bond. As astrophysicist Neil deGrasse Tyson once said, even across the void, Earth and Moon are still touching. It's a poetic truth built on physics. Their contact isn't through air or matter, but through gravity, an unseen hand linking their motion, their energy, and their histories together. So yes, Earth's gravity is still slowing the moon, and the moon is still responding. The two are partners in motion, locked in a slow exchange that continues to shape the length of our days and the rhythm of our tides. What looks steady in the night sky is actually a living system, changing moment by moment, proving that even stillness in space is never truly still. We've spent the last few chapters exploring how the moon became locked to Earth, how gravity slowed its spin until one side always faced us. But what if that balance was somehow broken? What if, suddenly, the moon began to spin again? It sounds like pure science fiction, yet thinking through this scenario helps us understand just how delicate and powerful the Earth-Moon connection really is. Let's imagine that a massive event, perhaps an enormous asteroid strike, imparts enough energy to make the moon rotate once more. The odds of that happening are extraordinarily small. It would take an object several tens of kilometers wide, striking at incredible speed, to provide enough torque to disturb the lock. Still, for the sake of curiosity, let's consider what would unfold if it did. The moment the moon began to rotate independently, the geometry of Earth's tides would change instantly. Our planet's oceans are tuned to the moon's fixed gravitational pull, the regular rising and falling of the tides, the pattern that guides ecosystems. navigation, and even human sleep cycles depends on the moon's constant orientation. If the lock broke, that rhythm would collapse. Tidal bulges would start shifting unpredictably. Some coastlines would experience unusually high floods. Others might see long periods of still water, sometimes called dead tides. The regular tidal calendar that fishermen and scientists rely on would become meaningless. Entire ocean systems could lose their steady mixing of warm and cold currents, reshaping marine life across the globe. The consequences wouldn't stop there. Earth's rotation and axial tilt are stabilized in part by the moon's gravity. The lunar pull acts like a weight on a spinning top, keeping our planet's axis from wobbling too much. Without that steadying influence, or with it constantly changing as the moon spun, the Earth's tilt could start to wander. Models suggest it might fluctuate between 10 degrees and 45 degrees over long time scales. A tilt like that would be catastrophic for climate stability. Seasons could swing wildly. Regions that are now temperate could freeze, while others might overheat. The cycle of ice ages and warm periods would lose its rhythm. In short, the predictable balance that allowed complex life to evolve on Earth could break down. Meanwhile, the moon itself would feel the strain. As it began to rotate again, internal stresses would ripple through its crust. The moon is a rigid, brittle world. Even a small change in rotation could trigger moonquakes, cracking and shifting the surface. Stored energy from billions of years of gravitational stress could be released, especially on the far side, where the crust is thicker and under more tension. Scientists estimate that even a slight increase in rotation, say, a change of just 10 to 15% in angular speed, would dramatically amplify tidal stresses across both bodies. Those extra forces would twist the moon's interior, creating heat through friction, and possibly awakening deep seismic activity. The same gravitational feedback would tug on Earth's oceans, intensifying tides and shortening or lengthening our days in unpredictable ways. Lunar phases, as we know them, would also vanish. The familiar pattern of crescent, half, and full moons depends on the moon's locked rotation. If it started spinning freely, the sunlight on its surface would shift continuously. From Earth, the moon's face would change not in smooth monthly cycles, but in chaotic, shifting patches of light and shadow. The visual anchor of our night sky would become unstable. The disruption would affect more than physics, it would touch biology. 2. Many species on Earth follow lunar rhythms. Corals release their eggs during specific phases of the moon. Birds migrate by its light. Even human sleep patterns are subtly influenced by the lunar cycle. A spinning moon would shatter that consistency, throwing countless natural rhythms into confusion. But nature, as always, seeks balance. Gravity is patient, and it never stops working. If such a catastrophe somehow occurred, tidal friction would begin the long process of restoration almost immediately. As the moon's new rotation interacted with Earth's gravity, friction inside its crust would again convert motion into heat, slowly draining energy from its spin. Over millions of years, the lock would re-establish itself. The moon would once more turn just enough to keep one face pointed toward Earth. In other words, the balance we have now isn't fragile, it's self-healing. The system always trends toward the lowest possible energy state, where forces are evenly distributed. A spinning moon might bring temporary chaos, but in the end, gravity would restore order. That's one of the remarkable truths of our universe. Stability often comes not from stillness, but from correction, even if thrown off balance. The Earth-Moon system would find its way back. So while the idea of a spinning moon makes for dramatic storytelling, it's a reminder of how precisely tuned our current world is. The moon's lock gives us steady tides, regular seasons, and a calm night sky. It anchors Earth's rhythm in a way that few other planets experience. If that rhythm were ever broken, our world would feel it instantly in our oceans, our weather, and perhaps even our dreams. But gravity would still be there, invisible and constant, patiently pulling both worlds back toward harmony. In the end, the moon's stillness is not weakness, it's strength. It's the natural endpoint of motion, the shape of stability itself, and even if the dance were ever to go wrong, the universe would make sure it found its step again. To the naked eye, the moon appears utterly still, a fixed, unchanging face gazing back at Earth. But if you could watch it closely over weeks, or months, you'd notice something strange. The moon doesn't hold perfectly still. It rocks gently from side to side and nods slightly up and down, as though breathing in slow motion. This quiet motion is called libration, and it's the subtle clue that reveals the moon's true movement. Libration is the reason we can actually see more than half of the moon's surface, although we often say that only one side of the moon ever faces Earth. The truth is we can glimpse about 59% of it over time. That extra 9% comes from these small oscillations, tiny wobbles in orientation that let us peek a little past the edge. There are three main kinds of libration: in longitude, in latitude, and diurnal libration. Each has its own cause, and together they create the moon's graceful, rhythmic motion. The first type, libration in longitude, happens because the moon's orbit around Earth isn't a perfect circle, it's slightly elliptical. That means the moon speeds up when it's closer to Earth and slows down when it's farther away. But its rotation on its axis remains constant. The mismatch between orbital speed and rotational speed makes the moon appear to swing a little from east to west each month, as if it's gently turning its head. This longitudinal rocking accounts for most of the extra area we can see beyond the central face. The second kind, libration in latitude, comes from the tilt of the moon's axis. The moon is tilted by about 6 7/10 degrees relative to the plane of its orbit. Because of this tilt, sometimes we see slightly over the moon's north pole, and at other times, a bit more of the south. Over a full lunar cycle, it looks as if the moon is nodding slowly, showing us first one pole, then the other. The third kind, diurnal libration, happens because of our own motion on Earth. As Earth turns, observers at different points on the surface view the moon from slightly different angles. When the moon rises, we see it from one side of our planet 12 hours later. When it sets, our perspective has shifted by about the width of Earth's diameter. This creates a tiny daily wobble, letting us glimpse just a little more of the lunar limb. When these three forms combine east to west, north to south, and the daily perspective shift, they add up to about 16 degrees of extra visibility around the moon's edge. It's as if the moon, ever so politely, allows us to look a little beyond its curtain, reminding us that it's a living, moving world, not a frozen disk in the sky. NASA's Lunar Reconnaissance Orbiter, with its laser altimeter, has measured these librations in exquisite detail. By firing laser pulses at the surface and timing their return, scientists can detect movements as small as a few centimeters. These measurements show that the moon's motion is incredibly precise, yet never perfectly symmetrical. Tiny variations in the timing and amplitude of libration reveal the moon's internal secrets, clues hidden deep beneath its surface. One of the most important discoveries from studying libration is that the moon's core is not completely solid. Data suggest it has a partly molten iron core, about 530 kilometers in radius. The liquid portion moves differently from the solid outer layers, creating slight changes in how the moon wobbles. Those changes, when carefully analyzed, help scientists understand the density and viscosity of the moon's mantle and the structure of its crust. Even the moon's gravitational field plays a role. Beneath the surface lie areas of higher mass concentration, known as mascons. These dense regions, left behind by ancient lava flows and impact basins, subtly distort the moon's gravity as the moon orbits Earth. These uneven masses affect the way it rocks and rolls, fine-tuning the pattern of its libration over longer timescales. The sun's gravity adds another layer of complexity. Solar tides, tiny gravitational pulls from the sun, slightly modulate the moon's libration angles over decades. These slow, almost imperceptible changes show how interconnected the motions of the Earth, moon, and sun truly are. If we could speed up time, compressing months into seconds, the moon would seem to sway in a calm rhythm, leaning forward, tilting back, turning ever so slightly, then returning to its original stance. To us, it looks perfectly still, only because our human lives are too short and our eyes too limited to sense that motion in real time. Libration serves an important purpose. It helps maintain the stability of the Earth-Moon system. The slight flexibility in the moon's orientation allows it to absorb and adjust to the constant gravitational tug-of-war with Earth. Without it, the stresses inside the moon could build up to dangerous levels. In a sense, libration is the system's way of breathing, releasing tension while keeping balance. The next time you look at the moon through a telescope, imagine that slow, graceful motion happening even as you watch. It's not static. It's turning, adjusting, aligning itself to the forces that shape it. We live within that rhythm every night, unaware that our quiet companion in the sky is in constant motion. As one astronomer once put it, the moon moves constantly, it only looks still because we live too slowly to see it. Libration is that hidden movement, the proof that even in the universe's calmest phases, there's always a pulse beneath the surface, and that subtle motion, more than anything, keeps the great dance between Earth and Moon beautifully, endlessly alive. When we look at the moon, always showing the same face, it's hard not to feel that there's something deliberate about it, as if this perfect balance were crafted by design. How can two worlds, separated by hundreds of thousands of kilometers, move in such flawless coordination, yet the truth is even more beautiful than design? This synchrony arose naturally, guided only by gravity, time, and chance. Tidal locking, the condition where one body always faces another, isn't unique. It's surprisingly common across the solar system. Most large moons are tidally locked to their planets. Jupiter's Galilean moons Io, Europa, Ganymede, and Callisto each keep one face turned toward Jupiter. The same is true for Saturn's Titan and Rhea, and even for Pluto and its companion Charon, which are locked to each other, orbiting like two dancers who never break eye contact. But Earth's moon is exceptional. It's far larger compared to its planet than any other moon in the solar system. The moon is about 1/4 the size of Earth in diameter and about 1% of Earth's mass. That makes their relationship far more intimate and interactive than typical planet-moon systems. Instead of a planet dominating a tiny satellite, the Earth-Moon system behaves more like a binary pair, two bodies orbiting a shared center of gravity. This unique proportion made the lock not only possible but remarkably precise. The mass ratio between Earth and the Moon allows angular momentum, the total measure of spin and orbit, to be exchanged efficiently. In the early days of their formation, that meant energy could flow smoothly between the Moon's rotation and its orbit until both settled into balance. As one scientist from NASA's Jet Propulsion Laboratory put it, the lock is perfect not by mechanism, but by proportion. It's not that the physics are different, it's that the scale of this partnership made the outcome unusually stable. The system found a natural balance point where the forces of rotation, gravity, and orbital motion aligned almost exactly. Statistical simulations show how rare that kind of long-term stability really is. When astronomers model thousands of possible planet-moon combinations, varying size, distance, and orbital speed, most end up unstable. Some moons spiral inward and crash into their planet. Others drift away and escape completely. Only a narrow range of parameters allows for a lasting tidal lock, and our moon falls right in that range. If the moon had been smaller, it wouldn't have generated enough tidal friction to synchronize with Earth. If it had formed farther away, gravity would have been too weak to slow its spin. But because it formed at just the right distance, with just the right mass, it had time billions of years for gravity's gentle hand to shape it into this near-perfect state. Even the moon's physical structure helped preserve the lock. The near side, the side we see, has a thinner crust, while the far side's crust is thicker and denser. This asymmetry makes the moon's center of mass slightly offset toward Earth, by about 2 kilometers. That offset acts like an anchor, helping the moon maintain its orientation. Data from NASA's Lunar Reconnaissance Orbiter and the Grail mission show how the moon's interior cooled unevenly over time. Reinforcing this asymmetry, the thinner near side allowed more heat to escape, while the thicker far side cooled more slowly. As the moon solidified, its mass distribution froze in place, locking in the gravitational balance that keeps one face turned toward us. So, the synchrony we see today isn't a coincidence. It's the result of countless natural adjustments that favored stability. Every wobble, every fluctuation over billions of years gradually dampened out, leaving behind a partnership that looks almost too precise to be real. This balance has shaped more than just the moon's motion. It has quietly stabilized Earth's own environment. The moon's gravitational pull helps keep Earth's axial tilt steady, preventing chaotic swings that could cause extreme climate shifts. Without the moon, Earth's axis might wobble wildly, producing seasons that vary unpredictably. Instead, our tilt remains around 23.5 degrees, giving us moderate, reliable seasons conditions essential for life to thrive. In that sense, the moon's synchrony doesn't just make the night sky beautiful, It makes our planet habitable. It gives rhythm to the tides, regulates our days, and even influences biological cycles in plants and animals. It's one of those rare cosmic relationships where physics, balance, and life itself all converge. Still, scientists are careful not to romanticize the numbers too much. The odds of this configuration forming are low, but not zero in the language of physics. Unlikely doesn't mean impossible, it means that given enough time, even rare events will happen somewhere. The early solar system was chaotic, filled with collisions and shifting orbits. Out of that chaos, a few systems inevitably found the balance we see here. Gravity doesn't plan. It doesn't choose, but it always follows mathematics. And over vast stretches of time, those equations lead toward equilibrium. The moon's lock with Earth isn't evidence of design. It's the natural endpoint of motion seeking rest, of energy finding the easiest path. In the words of NASA scientist Jack Lissauer, the beauty of the moon's motion lies in how nature finds harmony in randomness. What looks like a perfect alignment is, in truth, the slow work of physics ironing out chaos. So, when you see the moon tonight, glowing quietly over the horizon, remember, its stillness is not magic, and it's not coincidence. It's the result of billions of years of gravity's steady persistence, a perfect synchrony written by time itself. Every calm thing has a violent beginning. The moon, so steady and silent above us, was born from one of the most catastrophic events in Earth's history, a collision so immense it nearly destroyed our planet, yet somehow created its perfect companion. About 4.5 billion years ago, when the solar system was young and chaotic, Earth was still forming. Its surface was molten, its atmosphere thick with vaporized rock and metal. Then came Theia, a planet-sized body roughly as large as Mars, travelling on a collision course. The two worlds met at a glancing angle, each carrying unimaginable energy. When they struck, the impact released more energy than any explosion since the birth of the Sun, enough to melt both planets' crusts and vaporize vast amounts of rock. The collision tore away part of Earth's outer layers, flinging them into orbit as a ring of molten debris. For a brief time, Earth was surrounded by a fiery halo, a disk of glowing silicate vapor and molten metal stretching thousands of kilometers into space. From that chaos, the moon began to form. Within a few thousand years, gravity started pulling the molten fragments together, slowly shaping them into a single body. Piece by piece, the debris coalesced, cooling as it spun, until it became the young moon, an ocean of magma encased in darkness, orbiting its parent world. At first, the moon was unimaginably close, only about 22,000 kilometers away. From Earth's surface, it would have appeared enormous, filling half the sky, its molten glow bright enough to cast shadows. The tidal forces between the two worlds were staggering. Earth's gravity stretched the moon's still soft body, while the moon's pull dragged on Earth's surface, slowing its rotation. This exchange of energy set the foundation for the balance we see today. As Earth's rotation slowed, the moon drifted outward, conserving angular momentum, the universal rule that governs how motion and energy must balance. The system evolved naturally towards stability, each change in one body mirrored by a change in the other. Evidence of this shared history is written in the moon's very rock. When Apollo astronauts brought samples back to Earth, scientists discovered that the moon's isotopic composition, particularly its oxygen isotopes, was nearly identical to Earth's mantle. That means the moon wasn't captured from somewhere else. It was made from Earth itself. It is, in the truest sense, our planet's child. Newer theories, like the Synestia model, take this idea even further. They suggest that after the impact, Earth briefly became a huge, donut-shaped cloud of vaporized rock, a structure called a synestia. The moon may have condensed within this extended atmosphere, forming not beside Earth, but within it, before slowly drifting outward as the cloud cooled. In this view, the boundary between Earth and moon wasn't clear at all. They were one continuous mass, reshaping themselves together. Even after the moon solidified, the memory of that violence remained etched in its crust. Data from NASA's Grail mission show fractures deep within the moon's interior, remnants of early tidal heating and deformation caused by Earth's gravitational pull. Seismic data from the Apollo experiments confirm that the moon's interior still bears stress lines, echoes of those first turbulent centuries. The moon's asymmetry, with a thinner near side and a thicker far side, also traces back to this fiery beginning. When the two bodies were still close, Earth's molten surface radiated intense heat toward the moon, keeping the near side warmer for longer. That warmth affected how its crust cooled, making it thinner and smoother. The far side, facing the cold of space, cooled faster, forming thicker crust and highland terrain. That difference, frozen in place billions of years ago, still defines the moon's face today. In a way, the moon's current tranquility, the soft, unchanging glow we see each night, is the final stage of that transformation. It's the stillness after the storm, the product of motion that has slowed and settled into perfect order. The physics that govern this transformation are universal. Chaos seeks equilibrium, energy finds balance, and what begins in turbulence ends in calm. The moon's gravitational field still carries the fingerprints of that violent birth. As one NASA scientist put it, the moon's gravity field remembers every force that ever acted on it. Every crater, every variation in crust density, every scar beneath its surface is part of a record billions of years long, a record of collisions, heat, and tides, all resolved into the quiet stability we see now. If you could replay that story in fast motion from the moment of impact to the moon's first full orbit, you would see fire give way to glow, then glow to stillness. The moon would pull away, cooling, hardening, its chaotic spin slowing until it locked perfectly with Earth. Each stage would show energy turning into order, a violent dance settling into harmony. This journey from chaos to calm isn't unique to the moon. It's a pattern seen everywhere in the universe. Stars form from collapsing clouds of dust and gas. Galaxies stabilize after collisions. Even atoms find balance through the exchange of energy. The same physical laws that brought peace to the Earth-Moon system shape everything that exists. So when you see the moon shining quietly in the night sky, remember what it really is: a survivor of a cosmic collision, a monument to energy transformed. Its serenity isn't the absence of motion, it's motion perfected. The moon's stillness is the fossil light of catastrophe resolved, a reminder that out of destruction, nature always finds balance again. The story of the moon isn't finished, not yet. Even now, it's still moving, slowly drifting away from us at a rate of about 3 8/10 centimeters per year. That might not sound like much, but over millions of years, it adds up. This steady drift is a quiet reminder that gravity never stops working, and that the relationship between Earth and the moon is still evolving. The same process that once locked the moon's rotation, tidal friction, continues today. As Earth spins, the moon's gravity raises tides in our oceans. Those tides don't line up perfectly with the moon's position, because Earth rotates faster than the moon orbits. The tidal bulges are pulled slightly ahead, and that small offset exerts a forward tug on the moon. The result? Earth loses a little rotational energy, and the moon gains a little orbital energy. That exchange is why Earth's days are slowly getting longer, by roughly 1 7/10 milliseconds per century. While the moon drifts outward, energy flows from our planet's spin into the moon's orbit, and the two adjust together, always obeying the rule of conservation of angular momentum. But this process won't continue forever. Over billions of years, the exchange will slow down as the system approaches equilibrium. Eventually, Earth's rotation will slow until one side of our planet always faces the moon, just as the moon already keeps one face toward Earth. When that happens, the Earth-Moon pair will be mutually tidally locked, turning together like two gears that move in perfect synchrony. At that distant point, a single day on Earth will last as long as a lunar month does now, around 47 of our current days. The familiar rhythm of sunrises and moonrises will change completely. For one half of Earth, the moon will hang permanently in the same place in the sky, never rising or setting. For the other half, it will never be seen again. When that happens, the tides will fade away. The gentle breathing of the oceans that we know today, the daily rise and fall caused by the moon's pull, will gradually stop. The seas will grow still. The exchange of energy that has linked Earth and Moon for billions of years will come to an end. The system will settle into a final, quiet balance. If we could see that far into the future, the night sky would look strangely peaceful. No shifting lunar phases, no eclipses, no tides, just a frozen pattern of light and shadow. The moon eternally fixed above one hemisphere of Earth, its face unchanging, its motion complete, But before that happens, other cosmic events will intervene. About 5 billion years from now, the Sun will reach the end of its stable life and expand into a red giant. As it grows, it will lose some of its mass through solar winds, slightly weakening its gravitational pull on the planets. That will cause Earth and the Moon to drift even farther outward. The changing sunlight and shifting gravity could alter their orbits in ways we can only model, not yet fully predict. Some simulations suggest that as the Sun swells, it could disturb the Earth-Moon system, changing its rotation slightly or slowing the drift even more. But even in that distant chaos, one thing is clear. The Moon will not escape Earth. Its speed, though increasing with distance, will always remain far below the escape velocity required to break free from our planet's gravity. Instead, the outward drift will slow gradually, approaching a limit long before any chance of separation. The final act of this celestial relationship will be one of quiet stability. Earth and Moon, bound forever, orbiting side by side. One side of Earth will live under an eternal moonlit sky, while the other will know only the stars. The flow of tides will stop, the oceans will rest, and the last exchange of motion will fade into silence. To us, that might sound like an ending, but in the language of physics, it's simply balance achieved. Nature always seeks the state of least energy, the place where motion settles into harmony. The Earth-Moon system is moving inevitably toward that point, not toward death, but toward completion. Stillness in space, as one astronomer put it, is not death, but balance achieved. The same forces that once tore a piece of Earth into orbit, that shaped tides, seasons, and life itself, are slowly winding down. What began in fire will end in calm, and maybe, when that moment finally comes, if anyone or anything is there to witness it, they'll see what we see now and feel what we feel tonight. Oi, gratitude. The quiet understanding that from chaos came order, from motion came peace. The Moon's calm future isn't an end to its story, it's the perfect resolution of it. A world born from catastrophe, shaped by gravity, and stilled by time. So, as we close this journey, take one last look at that pale light in the sky. It has watched over every age of Earth and every life that has ever looked up. It will continue to move slowly, invisibly, until both worlds come to rest together, side by side, in perfect stillness. And perhaps then, as the Moon hangs unmoving above one eternal horizon, the most fitting way to describe that final piece will be this. The Moon never stopped moving. It simply taught the Earth how to fall asleep.